Hello and welcome to today's lesson on sensing circuits. Our learning objectives are to explain the design and use of circuits containing thermistors, light-dependent resistors and other circuit components for measuring and testing. Calculate the current, potential difference and resistance in DC, series and parallel circuits, such as those for testing and monitoring, and apply equations relating to potential difference, current and resistance. We're going to start by discussing some types of sensing circuits. For a start, the external part of the building is illuminated when a beam is broken by somebody passing through the beam. Which type of system would use this? This type of system would be used in a security light. When smoke enters a detector, a beam of alpha particles is cut to a detector and the alarm sounds. What type of system would use this? It would be used in a fire alarm or smoke detector. An alarm sounds when a beam is broken or when there is a change in temperature near the sensor due to infrared radiation being emitted. This system could be used in a burglar alarm. Thermistors can be used in sensing circuits to produce a change in the potential difference as the temperature changes. And this type of sensing circuit can be used in things like heaters, air conditioning units and thermostats. Here we have a circuit showing a power supply in series with a resistor and a thermistor. The potential difference across the thermistor, labelled here as V out, will change depending on the temperature. What would the potential difference here be across V out if R1 and R2 had the same value? Here we've got a potential difference of 12 volts across the power supply, and this would be shared evenly because of the equal resistance, so 6 volts across each. What happens to the resistance of a thermistor as it heats up? Its resistance decreases and the current increases. In this question, you're asked to find V out when the resistance of the thermistor is only 10 ohms and the resistor is at 30 ohms. This is a problem that we could solve with ratios, but instead we're going to look at solving it through the equations. Our first step to solve this problem is to calculate the net resistance. For a series circuit, we simply add up all the resistance of all the components in the circuit, so 30 plus 10 gives us a resistance of 40 ohms. Now we need to calculate the current, which is done by dividing the potential difference of 12 volts by the 40 ohms of net resistance that we've just calculated, giving us a current of 0.3 amps all the way through the circuit at every point. Now we have the resistance of the component and the current flowing through it, and so we can calculate potential difference or voltage by using the equation voltage equals current times resistance. So 0.3 times 10 gives us an answer of 3 volts. Sometimes you can see the answer to these questions using ratios. If the resistors are equal, the ratios in the potential differences is 1 to 1. If they are 2 ohms and 4 ohms, they are in a ratio of 1 to 2, and so are the potential differences. I'd like you to now pause the video and write in your books 3 examples of sensors that we use in circuits. You probably thought of thermistor and light-dependent resistor and may have thought about a pressure sensor or switch. Here we have a circuit with a battery, 2 resistors, P and Q, and an ammeter. We know that the current throughout the circuit is 3 amps and the resistance of the resistor P is 2 ohms. I'd like you to calculate the potential difference across P. Pause the video now and put your answer in your book. We can find the voltage by timesing the current, 3 amps, by the resistance of the resistor, 2 ohms, giving us a potential difference of 6 volts. Now we need to find the potential difference across Q. Once again, pause the video and put your answer in your book. Again, voltage is current times resistance, so 30 volts. Now I'd like you to write the ratio of the resistance of P to the resistance of Q and simplify it as much as possible. The ratio is 2 ohms to 10 ohms, which simplifies down to 1 to 5. I'd now like you to write the ratio of the potential difference across P to the potential difference across Q and simplify as far as possible. And the potential differences are 6 volts and 30 volts, so a ratio again of 1 to 5. Here's an example of an exam style question. In a sensing circuit of a coffee machine, the battery has a potential difference of 12 volts. The fixed resistor has a resistance of 10 kilo ohms. Calculate the reading on a voltmeter when the thermistor is at room temperature with a resistance of 100 kilo ohms. The first step is to write down what we know. The potential difference across the power supply is 12 volts. The resistance of the fixed resistor is 10 kilo ohms or 10,000 ohms, and the resistance of the thermistor is 100 kilo ohms or 100,000 ohms. Next, we need to add up the resistance of all the components to find the net resistance. So 10,000 ohms and 100,000 ohms add up to make 110,000 ohms. If we divide the potential difference across the net resistance, we will get the current of 0.00011 amps. Then by timesing the current by the resistance of the thermistor, we can find that the potential difference across the thermistor is 11 volts to the nearest two significant figures. I'm going to look at the problem again, but this time when the thermistor is raised to a higher temperature with the hot water, and therefore its resistance has dropped to 20,000 Hertz. The first step is to write down what we know. So I'd like you to pause the video now and write down all the key information that you have at this point. You'll notice that when it comes to resistance, I've changed the values from kilo ohms to ohms. I suggest you always work in base units. The next step is to calculate the net resistance. Once again, pause the video while you write this in your books. So the net resistance is the sum of all the resistances of all the components in the circuit, in this case 30,000 ohms. Using the net resistance and the potential difference across the cell, we can now calculate the current running through the circuit. Do that in your book while you pause the video. Potential difference divided by net resistance will give us 0.0004 amps. Finally, we find the potential difference across the thermistor. Don't forget to pause the video and write your answer in your book. Current times the resistance of the component gives us a potential difference of 8 volts across the thermistor. Looking at this circuit, you can tell it is a circuit designed to measure temperature because it includes a thermistor. What do you think this type of circuit could be used for? This is a pressure sensor or a pressure switch, which will turn on the device when it is activated. Slightly trickier now, but what could this circuit be used for? The variable resistor allows you to measure how much something's been turned by and can, for example, be used as a position sensor. What could this circuit be used for? The light-dependent resistor allows the circuit to detect light levels. I'd like you to pause the video now and copy this diagram into your books. We're going to use it again in a minute.
This question relates to the circuit diagram that you've just copied into your books. It's used to measure the intensity of light, and it includes a normal resistor and a light dependent resistor, or LDR. The potential difference across the LDR, V out, can be used to measure that light intensity. To start with, I'd like you to pause the video and write down the relationship between the potential differences in a series circuit. In a series circuit, the potential difference across the battery or cell is equal to the sum of potential differences across all of the components in the circuit. Carrying on with this question, I'd now like you to pause the video again and answer this three-part question. And here are the answers. Please make sure you mark your work and add any corrections if you need to. For the final part of this question, I'd like you to once again pause the video and then work through this part of the question. And here's your answer. Please make sure you mark your work and make any corrections if you need to. Well, that brings us to the end of today's lesson. I hope you found it useful, and thank you very much.